Welcome to IVA, all of you who are in the Wallenberg Hall at IVA, or also all of you who are now behind your screens. Today we will have the Society Forum that will address electricity supply to the growing ICT sector. This is something that is organized this year by three of our sections at IVA, one for electrical engineering, one for basic and interdisciplinary engineering sciences and information technology. Thank you very much for your efforts to get this webinar together. IVA is a meeting place, and of course, as we all know, just now meetings are a lot more complicated than they used to be. But we are a place where we like to collect people who have a little bit different backgrounds and who also consequently have different opinions about things and different ideas. And we believe that it is this dialogue and the debates that we have in our meetings that will bring all of us forward in our thinking and also towards different kinds of solutions that are needed in the society. So I look very, very much forward to this discussion today and hearing all of you in it. And also I hope that those of who you are behind your screens will be able to also participate in the dialogue and discussions through the interface that we have provided. So welcome again, all of you. And I give now the word to Birgitta Reesvik, who will lead these discussions today. Thank you.
Thank you very much, Tula. And I will also say welcome to all of you and to all the participants here in the webinar that we have arranged. My name, as said, I'm Birgitta Reesvik, and I'm the vice chair of one of the division electrical engineering that's been one of the organizers. And we have worked together to put together this program. I have a background in the industry and power sector, and I've been working quite a lot with climate and energy policies. But today, as said, I'm the moderator, and I will try to keep the timing, and I will see that we can pose questions and have an interaction, and also with you in the audience. And I like to share that we have this question via the menti.com, and I have some number here. You can note them down, 9532069. I will repeat that later on. Well, to the theme, ICT sector and energy. Of course, with the increased use of data and IT will, of course, increase the energy use to operate the total IT system. At the same time, we know now that during the corona situation that we had, that the digital world has really been the precondition for our distance work, our living, I would say, the education, get shopping and getting entertainment. We are all really connected and dependent on the ICT sector. And you can just imagine if we hadn't had it, how would the situation be then? But at the same time, we have had in Sweden a very, I would say, quite harsh and tough debate about and focus on the building of data centers in Sweden. And especially there's been some criticism that why should we build this data center in the middle and south of Sweden when we have the capacity problems with electricity, with weak transmission and so on. And there's also been an attitude, is this really worth it? We can use this electricity for other purposes, to the industry and so on. But we would like to get some more data and facts in this issue. Are the data center really the dominant energy user in the ICT sector? How important is the data sector for the digitalization of Sweden? And what about other parts of the ITC sector? How is this really distributed between transport network, routers, the mobile networks, compared to also to data centers? And what is also the CO2 footprint for all this? And at the same time, are there any technical reasons why it's important to locate data centers with short distances with the user? Is that a prerequisite for if we should have self-driving cars and so on? Is that an issue? Anyhow, there are many questions, and I know that we will try to get some more facts tonight, and I hope that we will get some more answers on different issues. So we will look at the electricity and energy use today and tomorrow for the ICT sector, the climate footprint, as said, and also the potential with new technologies and what is happening in the research area. Because we can look into how much energy is actually needed to transfer a piece of data, and what is the typical value today, and what is the potential for tomorrow. So we will cover a lot, and we have a full program, and as said, I invite you all to post questions at thementi.com, and we will forward these questions. So without further ado, I won't go into details with all the names. I think you all see in the program, but we will then start, and I think we just kick off the program and start with our first speaker, and that is George Kamiyaya, that is placed at the International Energy Agency in Paris, and I know that you've been looking at different projects and reports in this area. So please, George, start off, and I let you introduce a little bit yourself first. Thank you.
Great, thank you so much, Birgitta, and thank you to the Royal Society for the really kind invitation. It's a real pleasure to be here and to share some of the numbers that we have at the IEA. So briefly, to introduce myself, I work at the International Energy Agency. We are based in Paris. We're kind of a sister organization of the OECD, looking at all parts of the energy system. So, electricity systems, all end uses, industry, transport, buildings, oil and gas, all of that. So one of our big focuses is looking at energy and emissions, energy demand and emissions for climate change and clean energy transitions. So within the agency, I focus on that as well. So I'll try to go through my slides quickly. It's packed with information and data, so I'm happy to share links after, and really would like to dedicate the time to the discussion, which should be very interesting. So I'll get started then. So the first thing is that greenhouse gas emissions globally come from many different sources, and the bulk of those emissions come from the energy sector. So, you can see in this the chart that most from energy and industrial processes. Within that, there's emissions coming from power generation, from heavy industry, from transportation, buildings, which would include data centers and others. So the climate challenge is a complicated one because emissions are coming from so many different services, sectors, and end uses. So digital is one part of that. So if we look at the ICT sector, we think of data centers, data transmission networks, devices. So those have within all of those emissions, they comprise a certain share of that. They also have an indirect effect on other sectors. So if you think of a smartphone, for example, that technology, in addition to data networks and mobile data networks and GPS, have allowed us to have mobile transport services and shared mobility services like Uber that were not possible in the past. So these digital technologies are also having impacts on how we use energy services in other sectors. And those in turn can have other indirect effects. For instance, if we have Uber, that can change how traffic patterns evolve, the built environment, roads, transportation systems. So there's really these multiple layers that we need to think about when we talk about digital technologies. So I'm going to first focus on the direct energy and carbon emissions from digital technologies. A bit of context here in that digital technologies are really changing very rapidly. So, if you look at the number of internet users, it's grown by 10 times over the last 2 decades. Internet traffic is up, something like 2,200 times. And those, dwarf any gains or increases we've seen in population, GDP, or any energy indicator. So naturally, we would see these kind of headlines saying that, because the internet is growing so quickly that it's going to increasingly use more and more energy. So here's a headline from 1999 in Forbes, a U.S. Estimate saying that, this is from 1999, by the next decade, it would consume half of the U.S. electric grid, so by 2010. Obviously, that didn't happen, and now we're seeing headlines like this one based on the recent paper that Eric Massenet and colleagues published in the U.S., which actually showed that data center energy consumption was flat over 2010 to 2019. So in the graph on the left, you can see how internet traffic grew by 12 times, data center demand grew by 7.5 times, but data center energy use only grew by 3% from 2010 to 2019. And that there's really two main drivers here. So one is there's been a very large-scale shift from smaller, inefficient data centers, from so-called enterprise or corporate data centers to the cloud and hyperscale data centers. So these are, larger data centers that companies like Google or Amazon, Microsoft are building that can compute at a much higher efficiency than these traditional data centers, which, could be a small room inside of a company building using HVAC systems within that building and largely are underutilized. So that's one of the main drivers. So just for context here, data center energy use was about 200 terawatt hours globally in 2019, which is about 0.8% of global electricity use. So in the grand scheme of things, it's an important number, but also not as big as, if we compare it to other end uses like cooling. So air conditioning, that consumes about 2,000 terawatt hours a year. So about 10 times this amount. But it's kind of comparable to, a couple times more than electric cars today. So just to give you some context there. The other major trend that we've seen is huge energy efficiency improvements. So the so-called Kumi's law, which shows that, the efficiency of computing has been doubling every 2 to 3 years over the past few decades. And on the right graph, you can see a study recently by Josh Aslin and colleagues showing how data transmission networks of well-managed networks in developed economies have been doubling every couple of years as well. So very strong efficiency trends. And, coming from the energy sector compared to any other end use, this is a very rapid pace of efficiency improvement. Of course, so they're working a lot to reduce the amount of energy that's needed. The other is how do you supply that energy? So these ICT companies also happen to be leaders in corporate renewables procurement. So this is data from Bloomberg New Energy Finance showing that Ict sector actually accounts for about half of global corporate power purchase agreements signed over the last couple of years. But there's a big caveat here in that, companies like Google and Apple have achieved and set targets around 100% renewables. So what this means is that they are buying enough renewable energy or generating it on site, mostly it's through power purchase agreements, to offset the amount of electricity that they're consuming in their operations, mostly for data centers. So, for instance, Google, I think, consumed about 12 terawatt hours in 2019. That means they would have had enough contracts to generate 12 terawatt hours of renewables. But of course, electricity systems are very different throughout the world. So here's a map from Google showing that, in sites like Oklahoma, because it has a lot of renewables, low carbon electricity, and they're able to kind of shift their demands around, 96% of their data center electricity use is clean. But if you look at Singapore, obviously they're constrained with natural resources and renewable access. So only 3% of their electricity supply is powered by zero carbon electricity. So there's this one challenge of meeting 100% renewables on a purchasing basis. But I think the decade ahead will be quite interesting because companies like Google, Apple are looking beyond that. So how do they match their demand to match with clean electricity available on the grid? And then also looking at their supply chain as well. So thinking beyond their own operations. So I've just really talked about the use phase, but really I think we need to also keep in mind that there are environmental impacts and energy use impacts throughout the life cycle of a product. So especially as the device gets smaller, it's dominated by the raw materials extraction and manufacturing phases. So if you look at the latest Apple iPhone environmental footprint, about 80% of the environmental impacts are coming from those first two phases, not from the use phase that the consumer sees. Of course, there's other impacts to the environment, impacts during materials extraction to soil, air, water, biodiversity, air pollution issues, water use, and of course, electronic waste. So I'm going to shift gears a little bit, talk about a specific use case. So you may have seen headlines like this one saying how Netflix emits, 1.6 kilograms of CO2 for every half hour, which is a very large amount, equivalent to driving almost 4 miles. So I published a fact check earlier this year. You can access it on our website. But in fact, this number was overestimating the value by 40, 50, 60 times. So they've actually corrected their value since to bring it down by 8 times. But still, the main message here is that these kind of headlines are quite dangerous in that they don't understand they've taken assumptions from years ago and applied it and misconstrued some of the research that was done earlier. And of course, thinking broadly about our own digital and carbon footprint, this is a very small energy and carbon intensive activity compared to other activities like driving. So we need to keep that into context as well. So looking into the future, here's another headline from The Guardian predicting that a tsunami of data could consume a fifth of the global electricity by 2025. We need to understand that journalists are interested in kind of these headline-grabbing numbers, but realistically, coming from the energy system, for a sector to go from about 1 or 2% to a quarter or fifth of electricity supply within the next few years is not really reasonable. And you can see in this graph that there's a range of studies that have been published looking out in different time horizons. And this Guardian headline picked one of the worst case scenarios from a 2015 study. But of course, since then, there's been updated studies showing that actually the energy use is lower. So, here's a comparison of those 2015 numbers versus more recent research and then some of the other papers that are out there. So I think it's important to think about this. There's an immense challenge, I think, in trying to predict what's going to happen over the next decade. So if we think about the last decade, we had 3G, 4G emerging, and then new uses of like streaming video, which are very data intensive activities, but offset by strong energy efficiency improvements and strong decarbonization policies. But of course, there are emerging technologies like blockchain, machine learning, 5G, the Internet of Things, augmented reality, and eventually newer generations of technology. So it's incredibly challenging to try to predict what would happen in 2040, much less 2030. And I think it's important to keep in mind that the digital technologies is a very different beast in terms of energy modeling than conventional sectors that we have a better understanding of. Here's an example looking at Bitcoin mining. This article predicted that it would consume all of the world's energy by 2020. Of course, that hasn't materialized. But I think it's important to mention that, technologies like blockchain cryptocurrencies can grow very rapidly. So, over the course of 5 years, it's grown to, consume 60, 70 terawatt hours of electricity, which is not insignificant. But of course, the hardware is getting more efficient. So the other side of the equation I'd like to talk about is the effects that it has on other sectors. And arguably, I think this is a very interesting question and quite significant in terms of the global clean energy transition. A good example, I think, here is, what we're doing now, kind of like often we're teleworking if we can. What does that mean for energy use overall? So how does the ability to telework now affect other sectors? So the main 2 parts of this energy equation come down to how much energy increase is happening in your household. So because now you're heating and cooling your home using additional appliances. But of course, that's going to be offset by reduced energy use for commuting. But again, that depends whether you're commuting by car, usually, the distances you commute, maybe you bike or cycle, so those reductions are small. And of course, the frequency at which you telecommute and whether your office can eventually, make it smaller or shut down, changes the dynamics of the commercial building energy use. Of course, there are longer-term permanent secondary effects, structural effects like, if we are able to telework all the time, will we be willing to move further away from cities into larger homes and adopt different transportation patterns? So a couple of years ago, we looked at how digital technologies could be applied in the energy sector to reduce emissions, to improve efficiency. You're welcome to look at that report. It's called Digitalization in Energy. There's a lot of applications throughout all the sectors, end uses, electricity and oil and gas. I think the main point I'd like to highlight on this slide is that really it depends, the application of these technologies really depends on climate policies. So unless we have good climate policies, digital technologies could easily be applied to actually increase emissions. So if you think of automated vehicles and we don't have climate policies, they could actually be increasing how much vehicles travel. They might not be electric. They might not be shared, or easily applied in oil and gas sectors and actually making it easier to extract oil and gas, or applied to extend the lifetime of coal plants. So I think it's really important there to think about the broader climate energy landscape. Just to wrap up, a couple things related to the energy sector that we need to think about is that there's a lot of existing infrastructure. So we need to think about the new infrastructure that we're building. For example, if a coal plant is built in Asia today, it's going to probably last 50 years, so 2070. So we can't be building new dirty sources of electricity or transportation. The other challenge is that we need to also rapidly scale up innovative new technologies. And I think this is where digital technologies can play a huge role. So, our recent Energy Technology Perspectives publication looked at, to get to net zero by 2070, about a third of emission reductions come from early stage technologies. For 2050 net zero, it means almost half of those emission reductions are coming from new technologies. And for particularly hard to abate sectors, so if you think of heavy industry or long distance transportation, even a larger share, so 75%. So this is where digital technologies, I think, could play a very important role. So my last slide is really kind of these two sides of the coin that we need to think about. So how do we reduce the direct emissions from ICT? So I think we could all play a role as users. Data scientists could play a role. Companies can play a role. Governments can play a role. And then how do we apply those digital technologies in the right places to reduce emissions in other sectors? Because arguably this is where we can have huge impacts in terms of achieving our climate targets. And I think governments really have a central role to play with concrete and ambitious climate policies, companies working with digital companies, energy companies, and of course the experts applying their technologies to help kind of accelerate clean energy transitions globally. And I'll end it there. There's some readings there if you're interested in more information. Thank you.
Thank you very much, George. It's really a good overview. It's so much information you're giving. But I know that we also can have some comments on this. And I know that Andrei, you were actually in one or two of this diagram that George showed. Anders, are you there?
Yes, I'm here.
Yes, you're there. Okay, good.
Yeah. These.
Yeah, you can go on if you have some comments, Anders, directly to George.
Yes. Yeah, of course. These publications of mine, they are still seemingly going strong. The research world won't let go of them. I don't know what I've done. Maybe something right, perhaps. You mentioned a lot of things here. So what are the data sources for what are your own modeling of these 200 terawatt hours? And the sources of that. And the CUMIS reports and papers, they have received a lot of criticism for their scope. So you have many other new papers.
Anders, can I just interrupt? Yeah. Can I just interrupt, Anders? Yeah. Could you put on the video? It's nicer to see you, if it's possible, than just the black screen.
Yeah, okay,
oh,
of course.
Now you're there. Good.
Yeah, you have me here. I mean, this is the modeling is a little bit untransparent if you just use some sources and say some sources are wrong and some are right when you have not probably done the measurements. Or maybe you do the same thing for lighting and cooling, the same modeling for the ICT sector. Or you just trust some sources. That's one point. And you have the CUMIS law. Is it still going strong? Is it still? He doesn't comment on that in this latest paper about data center recalibration. his Coulomb's law of the joules per computation. And the joules per computation in hyperscale, what is it exactly? How far from the Landau limit are we, in the hyperscale? You mentioned something 2,000 exabyte. Where is that number from? Yeah, just to start.
That was some of the data, but maybe start off, George, about the model and so on. Can you just describe?
Yeah. So for the model, I mean, we're using the LBNL model. So we're using Eric Massenet's study, which includes John Koomey. And they've been pretty transparent. You can download their spreadsheet assumptions through their paper. I guess you can pick those apart and look at the assumptions behind those. But I think that's from what I've seen, it's the most detailed bottom-up study that I could find. There are other papers out there, like there was a paper out of Canadian researchers at McMaster that projected out to 2040, but I dug into those numbers, and it's actually just an extrapolation of 5 years of data growing at a certain rate, 12% or something, and they just extrapolated that into the future, which doesn't really take into account those kind of efficiency improvements that we're seeing. So on the modeling side, we're just using Eric's numbers. And then on Koomey's law, I mean, it's a great question about when we're going to see these limits to efficiency and slow down. So, I mean, that's one reason why we only have charts that going out to 2022, 2023. Because I don't really have any confidence in predicting anything in 2025, 2030, 2040. And maybe the question really should be around what can we do given the risks of approaching efficiency limits, and how do we invest in the right technologies and innovation so to avoid those. So from the IA, we come from more of a policy side as well. So we're trying to push out messages that, innovation is very important. Companies and governments should be not relying on these efficiency gains continuing forever, because, so far it's been okay, but, in the next couple of years, soon we might see demand outpacing efficiency improvements if we don't see more investment in more new technologies that can get past efficiency challenges that current technologies might have. And of course, the other side of the equation is how do we supply those infrastructures with clean energy?
But you have a lot of problems. I mean, with this bottom-up approach for US only, and I mean, this is you have now a new article from Beijing Research Institute of Artificial Intelligence having 500 terawatt hours already now. Still small, and in the greater scheme of things. But I mean, I think as a policy institute, you should have a broader look at what is out there. I mean, I am a small player nowadays in this emerging field of research looking at this issue more with the research method. Totally. I mean, they have a US perspective. They forgot the Chinese data centers when they presented their paper in Science. So I reviewed their paper, I can admit now, and my reviewer comments were not addressed.
Okay, this might be a bit too into details, but I understand that you are not aligned. But you have another figure then, Anders, that you think is more realistic in 3 years' time, or what?
Yeah, I mean, now it's probably higher than 200 terawatt hours for 2020 globally. The data centers, they are not the biggest part of the total ICT ecosystem, but definitely it will rise many times to 2030 already. Okay. That is, you can have 5 or 6 different modeling approaches, easily explained, which can show this. So this is clear, and that is interesting how some modelers can come to flat maybe to 2030. That is just 10 years, less than 10 years away.
Okay.
So we know about the bits, we know about the system support and total number of instructions, computations possibly generated. And you have already, as you said, Bitcoin is already 65 terawatt hours. So So Bitcoin, would Bitcoin then be almost half of the all data centers now? George, this is something for you to think about.
That 200 terawatt hours does not include Bitcoin. So
that's excluded.
It depends whether you consider.
Yeah.
Okay. Great.
Yeah. I mean, if you consider Bitcoin as a data center, I guess you would add that, but.
It's not really that, I think. But anyhow, I think that's a good start for temperature to go on and dig further into some other aspects. And we will continue to have possibilities to question. And I would love you, George, to still be on and listen. So now we go further to some facts about life cycle analysis and so on. And this we have. Jens Malmudin, Malmudin, yes, from Ericsson. And please introduce yourself a little bit. You're welcome.
Yes, thank you, nice to be here. Yes, I'm Jens Malmudin from Ericsson Research, and Ericsson's main product is base stations, which you see here up on the roof on this building. And I will talk about the energy consumption and carbon emissions in the ICT sector. So I will focus more on the direct emissions of the ICT sector itself. So George painted the larger picture, and now I will go a little bit more into the details. So let's first look at how we define the ICT sector. We keep this definition that ICT is the combination of IT and telecommunication, IT and communication. ICT. So networks, data centers, and all the devices. And then we have a closely related sector, entertainment and media, which is entertainment, music, film, and media, TV, radio, and paper. Of course, we have a lot of other electronics. And we can see two long-term trends here, that entertainment and media are more and more sort of included in the ICT sector. We use the ICT devices, the platforms, to consume entertainment media, and that has become a big part now of ICT. Another trend is that we built in the ability to communicate into most other electronics. It is very beneficial for a lot of electronic products, like appliances or in buildings, meters, utility sectors, in manufacturing equipment, and so on and so on. So, for about 15 years now, we have collected a lot of data to be able to calculate or estimate the energy and carbon footprint of the ICT sector and the entertainment and media sector. And this is what we've seen over these years, that both these sectors grow from about 2005, well, they had been growing up until then, up until about 2010, when there was a lot of good trends happening more or less at the same time that kept both these sectors, at least the entertainment and media sector, from growing anymore. And in fact, the total combination of these sectors started to decrease. And the reason was that TV sales and PC sales they peaked and started to decline. And we see that one important thing happened here, the introduction of the smartphone, and that was very important. So a lot of consumer electronics, which used to be individual products, we all bought, now was included in the smartphone. We also saw that a lot of paper media was moving online, and we also saw that the display technologies became more energy and material efficient. So up until 2010, the larger TVs we bought consumed quite a lot of power. But today, a new 50-inch TV consumes less than a large, thick 32-inch TV. And within the ICT sector, usage has moved from PCs to tablets and smartphones. And so on and so on. And this is the total carbon footprint you see here. It also includes the embodied footprint, so the manufacturing of all mobile devices, the network, and the data center and service and so on. That was the story up until now. And then this year has been nothing but normal. So during COVID-19, we have seen a large data increase. And during this time, we have asked all the network operators, data center operators, to look carefully now. What happens with energy consumption? And this is a statement for GSMA. They say that in most cases, network electricity use has remained flat, even as voice and data traffic has spiked by 50% or more. So in fact, this year, the data consumption of global is about 50% higher than it was last year, and about 25% more or less happened overnight in the spring. And why we talked about Anders and George talked about data and why should you believe our studies? And I'd say it's because we collect a lot of data it's real measured data by the operators all around the world. This is an example for European operators. So about half of all the operators in Europe have been providing detailed data for our studies. We are able to see the mobile networks, the old telephone network, as you see here, is still consuming quite a lot, although it's seldom used anymore. It's old technology, still consuming because we want to keep it there. And that is, of course, something we can prove in the future. And as you can see, the number of subscriptions have been fairly flat as the electricity consumption, but the data has kept increasing all the time without impacting the electricity consumption. And this is what we're seeing. This is brand new figures with the COVID-19 impact included. So we see that compared to the estimate before COVID-19, we have estimated that the CO2 emission will go up about 3% and energy will go up about 5%. But as I said before, the data increase is about 50%. And you can also see the parts here. Data centers, networks, more or less the same, and combined they are as large as user devices. But user devices is the main part, the main source of emissions for the Ict sector. And half of that comes actually from the manufacturing of all the smartphones and so on, PCs and that. Also compared here is the TV networks and TV peripherals from the entertainment and media sectors, the largest part of the entertainment and media sector. And during COVID-19, the increase is more to do with that we're using PCs, smartphones and so on, a little bit more, about 10% more will be over the full year. But TVs have made a strong comeback. So TV use used to decrease year by year, but now it's up. We think that it will be up like something around 20% over the full year in the world. And which of course lead to more electricity consumption, more CO2 emissions. So one of the false comparison going on in the world have been between the ICT sector and the aviation sector. But as you can see here, the aviation sector, all of aviation is about 2.5 times as large as the ICT sector, if you include all aviation and all the high altitude effects and so on. And now we can see that during COVID-19, it's estimated by International Energy Agency, George and colleagues, that the emissions will go down by 60% for the full year. It was down by 90% in April after the lockdowns, in the lockdowns. And here we can see that when you actually don't fly, you reduce emissions. If we would try to stream less and so on, it wouldn't reduce emissions unless we switch off the networks and the data centers, which we can't do because then everything more or less will turn black in society. So it's not such a good idea. And it's also, we can see that we can actually stream more and use more video conferencing and so on without increasing emissions so much. That's how the networks and data centers works. So this is what we've seen when we are looking at the footprint versus the data. So it actually showed that data, the tsunami of data happened 10, 15 years ago. And then it has slowed down. Last 10 years, it grew by 12 times. And CO2 emissions were flat over for a decade. And in the future, the uncertainty here is how much data traffic will we have? It depends on how we manage to improve the technology. So data is a function of technology. When it comes to energy and CO2 emissions, it's more related to how many subscribers, how many humans are we on the planet, which is much more stable. Because I think we will continue to use PCs, smartphones, and so on. There might be some new equipment that come in here, like some VR headset, that may actually reduce the footprint even more, because then we could switch off all the big screens. We don't know that. We never anticipated what would happen when the smartphone came. So I will go a little bit I have some 2 minutes maybe. So let's look at some numbers. Sorry, wrong numbers. You have seen in media about when we stream video. And if I look at, for instance, we have an example of if you download Despacito, all these views of this music video consume 1 terawatt hour. If you look at, take the video time and so on, you get to 2,600 watts. That's impossible. You can't consume that when you're looking at the video on a smartphone. And it's not any equipment in the network that consume this. So this is about 100 times too high. And you have some other examples here. George mentioned the Shift product, 6 kilowatt hour for streaming Netflix. That's 6,000 watts. The TV only consumes around 100 watts. And there's no equipment in the network consume that much. A core router, but in Sweden there's only a few core routers that actually handles the internet traffic in and out of Sweden and across the big cities. And one main wrong assumption here is that power is proportional to data. This is wrong. And this also leads to the false perception that the ICT's energy sector grows and can grow a lot in the future. So let's look at how real figures look like. And you can actually go home and measure a home router, and you will probably see it's around 10 watts. It's around 10 watts all the time, no matter if you are streaming or not. It has to keep the Wi-Fi open and the 4 ports open, and always listen to the WAN, and the line itself consumes around 5 watt. And actually, the data transmission and IP core network are very efficient. Here we can have gigabit traffic for 1 watt per port, but of course you will travel through many of these ports. So, in the end, if you stream Netflix, you will consume around 18 watts if you put these together. And it's actually it's less than 1 watt you are adding in electricity consumption. So, then in the end, you have the data centers. And we know the Netflix figures. If you take all their energy consumption, so it's also the production office and all the streaming engine, including their use of the Amazon platform and similar platforms, it's only about 5 watt or less. To actually stream in optimal conditions, consume less than 1 watt. So actually, when you stream, the delta, the added electricity consumption, are less than if you would turn on an optical disc player. So actually, streaming is more efficient. And when we stream, we can actually stream to a smartphone and switch off the TV. So now we can start to save a lot of electricity. So this is the true numbers we should look at. It's not thousands of watts, it's tens of watts or even lower. The data centers, we talked about where are the figures. These are, when we do studies, we look both on all servers produced year by year by year. And it's around 11, 12 million year by year. And the lifetime is about 4 or 5 years, so it's about 50 million in active use. These are the big data center companies. They consume about 57 terawatt hours, these 22 companies. You have all the big ones here. This is for year 2018. It goes up a little bit. They run mainly on renewables, as you know, Google and the other ones. And the total footprint, 12.5 million tons. It's only 0.02 of the global carbon footprint. And these data centers represent the majority of the data traffic in the world. You have all the search engines, streaming platforms, the operating systems, the app stores, and so on within these data centers. If we take all the data centers based on the both top and up down, it's a slightly more than 200 terawatt hours. We also include offices and stores for some companies here, and there's some overhead, business travel, and so on. And so the carbon footprint is about 0.2%. And I can also say, if I compare to aviation again, I can say that these top data center companies, they emit as much carbon as we Swedes do when we fly a year. So both we used to, before COVID-19 that is. And Netflix, actually, their total global platform, including all the Open Connect at the edges and the Amazon and so on, consume less than half a terawatt hours. They consume less than the airport Heathrow in electricity consumption. So I think the numbers are pretty good for the ICT sector, and it's such a shame really that all these big numbers are in media when that's not the truth. Thank you.
Jens, I just have a short. I mean, why do you think this has been? Why has the ICT sector this bad rumor then about this? Was it that you couldn't predict this development of technology?
I think it has stayed like that since 15 years ago when we did the first studies, and then we could see the sector was growing and quite fast. So we were, of course, worried that it will continue to do so, and projections back then, a few years into the future, also had this curve. But in 2010, it shifted. And I think that anyone can see this shift also at work and in your home. I mean, we used to have a desktop PC, but now we have a small laptop. And now we got the smartphone. We can use the smartphone for a lot of things now. And then we can turn off these other things. Okay, for the network, it has been slowly increasing. We are building out network. But I would say for network, we have a lot of data. We are actually measuring most of the networks in the world today, included in this data. Data centers have always been a little hard unknown, but I think today there's a lot of, I mean, these data center companies are very transparent with what they do.
Yeah, okay.
And there are survey sales statistics and so on and so on.
And I mean, this good CO2 numbers or footprint, you can say that has been more or less flat. And how much is then dependent that they are buying now renewable energy, these centers? Or is that the main reason why it hasn't decreased? Or
it's also that the grid itself has been a little bit, it's going down now. There's more solar and wind in the grid mix, but and the companies have buying, and you can see it in the last year's figures. It going down now. It started actually to go down. Before COVID-19, we said that it has gone down with 5% since 2015. Okay. Actually, but now with more use of PCs and so on, it's nearly up again.
Okay. Anders, are you there?
Yes.
Yes.
I am here now.
Do you have any specific comments to Jens?
Yeah, not really, but of course this is a very complicated system, and this division between entertainment media and ICT, it's a little bit difficult to understand. I mean, maybe you should look at the internet itself, a top-down approaches also, because there are so many devices and we don't know how they are used exactly and so on. This kind of total traffic, instructions, computations, whatever, and a total, more top-down, so you capture everything in this sector. That's some idea to look at this also and compare. And then you have this lady, we met her November last year, Livia Cabernard, had the 1 gigaton for all electronics production, and you have less than 0.2 gigaton for almost all electronics in the world, which is in media and the ICT. That's a quite big difference. 200 million tons and 1,000 million tons of carbon emission. So that's interesting to comment on that. And then this COVID. Yeah, we have discussed this also. Isn't this that this equipment have just absorbed this traffic increase? You still need to build new ones, for the future anyway. Or do you think we can keep without building new? And then I think that the one other thing I thought about, I think if you have 800 mega huge data center consuming 500 megawatt each in 2030, or let's say 60% of their capacity, how many terawatt hours is that rates compared to your flat rate for the data center. Or I mix a little bit your prediction.
Okay,
for
I
the
think
trade.
we
The interesting thing is the future. Prediction is the most interesting.
Okay, we stop there. Jens, comment.
I think the future, we need to, if we understand what has happened in the last decade, I think that is the key to the future. And it's easy to just predict things in the future, but I think you need to look at, okay, what has happened? Were we able to do this? And what was the underlying, we have the business model. It's very important. I mean, if you predict that everything will sort of rise like this, then you would also have an exponential cost of things. And I'm not sure that all the customers are willing to take that. And
they are paying millions of dollars for training AI models.
But when it comes to the situation now, Anders, I think that we try to collect as much data from the real world as possible and look at that. And you mentioned Carbonade, this study. That's a very rough way of trying to estimate the manufacturing footprint. So we have data for more than 3/4 of all the big ICT companies, display manufacturers, integrated circuit manufacturers, and so on. And when she do this economic input-output rough analysis, those sectors are not divided into exactly the ICT sector and so on. It's a very rough sector. This is the big metal sector. And you know as well that the metals the ICT sector are using is nothing. I mean, it's a lot of very specific metals where we pay a much higher premium price. And it's sort of like a sports car. A sports car has a lot higher absolute CO2 footprint, but compared to per dollar, it's much lower. So an economist would say that, we should buy a sports car because it has a very low CO2 value per dollar. Okay. And when you just assume that everything is flat, it's the same CO2 per dollar, I mean, then you can arrive at such conclusions. But they are very wrong, I would say, when you actually try to do a detailed study of the manufacturing sector, the manufacturing of the ICT sector.
Thank you very much. I think we have a question from the audience, Linda.
Yes, we will try to. There's one question that should not the focus be on energy per computational load? That's what's at the core of the problem. Is there anyone who wants to comment on that? Maybe George or
I can comment on that. And I think, I mean, it's when we are looking at the networks, they are dimension for peak hour. But if we really want to save energy, we should not look at the peak hour. We should actually look at why are they consuming so much when they are not used that much. And now we have been introducing sleep modes in the network. You can turn down, turn off, or go to a lower capacity and so on during nighttime, for instance. And by that, you can save a lot of energy, both in data centers and in the networks. And I think that's the key to save energy in the future. Another key is to shut down old standards, like the old telephone standard. Now we are trying to shut down the old 2G and 3G standards for mobile, which can save a lot of energy, and or make room for 5G without 5G will adding much more energy. It can actually stay in the same energy footprint. So of course we should try to be best at peak hour and performance and so on, but it's the complete picture tells us actually no, we need to be good also in these other parts because they are actually more important. Like your home router. It runs on average less than 1% of its capacity, but it's consuming 10 watts all the time. So what can we do there? We can actually get rid of it. We don't need it.
Actually, that was one of the other questions also. I think maybe we should move on in the program and then we get back to the questions.
Yes, we can do that. So, and now we are going actually to see on the entertainment side. And we have I would say a presentation from the SVT play, and this is Hilda Stenberg and Andreas Bjärlestam that are are presenting what SVT Play is doing and how they are looking at this to do it more energy efficient. So please.
Hi, my name is Hilda Stenberg and I work at SVT as a development manager for the webcore area.
And my name is Andreas Bjallestam and I work with SVT Play as a software engineer in the SVT Interactive department.
For those of you who are not familiar with SVT Play, it's a streaming service for watching TV over the internet. To get an overview of the amount of users, SVT Play has more than 1.3 million active users per day. Every day, more than 4.2 million video streams are started. Let's take a look at what happens when a user starts SVT Play. When the user starts a video, a lot of data is sent from SVT servers to the user's TV, computer, or cell phone. This data will pass through network equipment, radio base stations, routers in your home, etc. Throughout this entire process, there is equipment that consumes power. The amount of power needed to play a program depends on several different things. A TV, for example, consumes more power than a cell phone. Mobile networks consume more than optical fiber networks, etc. A rule of thumb is, however, that the more data that is being sent, the more power will be consumed. Sending a video stream requires a lot of data compared to, for example, an image or a web page. On average, 1.5 petabytes of data is transferred from our service every day. This is quite a lot and it requires a lot of energy. So what can we do to minimize the energy consumption for SVT Play? The things we can do that will have most impact on energy consumption is to minimize the amount of data that needs to be sent over the network. And to do that, we put a lot of effort into investigating the latest and most efficient technologies. Here are some examples of what we do.
Most of the data that is sent over the network from our service consists of video streams. So adjusting those will have the biggest impact. Adaptive streaming is a technology that we have been using for many years now. It means that the video streams are automatically adjusted to your screen size and the available network bandwidth. So, for example, when you watch a video on your mobile phone, you will get a smaller stream with lower resolution than if you're watching it on your TV, for example. Another example of a new technology that we are implementing right now is a new video encoding format called HEVC, or high efficiency video coding. This new encoding format can enable up to 50% size reduction compared to previous format, especially for higher resolutions. While the absolute majority of the data that is sent consists of video streams, we also do optimizations to other kinds of data. For example, we optimize the images that are used to present our content. And we do that by investigating and using the latest and most efficient image formats, such as WebP and AVIF. Here we can achieve a 30 to 50% size reduction of the images compared to traditional JPEGs. These optimizations that we do will also improve the user experience. For example, the videos will start quicker and have less interruptions. Also, many users have a limited data plan on their mobile subscription, so they will be happier as well. At the same time, people are buying new TVs with bigger screens and higher resolutions. This creates a demand for higher quality video streams, which in turn requires more data. Streaming of a 4K resolution video, for example, requires much more data than traditional HD or lower resolutions. One idea that we have been thinking about here is to show the user how much carbon dioxide emissions the different choices of streaming qualities produce. Just like some restaurants show you the carbon footprint of the different items on the menu, we could give similar hints to the user and let them choose depending on their current needs.
Finally, we can conclude, with the amount of users that we have, even small savings can have a big impact. We try to optimize on many different levels while balancing the user needs. Often the optimizations we do to improve user experience also will minimize the energy consumption required. Thank you.
Thank you from SVT Play. And sorry, but we don't have any possibility to pose questions to them. But I hope that was giving a bit of facts, what is happening also in the entertainment side. But now we have looked at the whole picture, we have dig down to the different technologies in the ICT sectors, now the entertainment business, but now we like to go a little bit further, what is happening in Sweden. And now we also for the data center and so on. So first we will start up with the introduction speaker, and that's Maria Sundval. She's the managing director for Equinix in Sweden. And after Maria, Thomas Soloniti will come from the Business Sweden, and then we will pose questions together for both of them later on. So please, Maria, start off.
Good afternoon, good evening, everyone. My name is Maria Sundval. I am the Managing Director of Equinix in Sweden, and it's really an honor for me to be here and talk to you all today. I have an engineering background myself from KTH, and so it's really a pleasure to be here tonight. I am going to talk about the colocation data center business and the role that the data center industry plays in the society today and for digitalization. So let me just share my screen. Digital is transforming markets. Digital is transforming industries, and digital is transforming our business model. And it's no doubt that the conditions for companies and their leaders have changed very much over the past years. First of all markets are now global. And regardless of industry, companies need to create digital products, and they need to understand how to launch these digital products and services on a global scale, and maybe also in markets where they've not been present before. And this completely changes the requirements for the digital infrastructure a company must build. First, some definitions. When I'm talking about a traditional data center, it is an enterprise data center that was normally located in the basement of the company. Hyperscale data centers are data centers like the very large ones operated by Amazon, Microsoft, Google, Facebook. A colocation or retail data center refers to a service provided by a company like Equinix. we normally host several customers in one data center. More than 50 is not uncommon. And often the enterprise is owning the equipment, and we provide the space, the power, the connectivity to network service provider. At Equinix, we take it one step further, and we provide connectivity to the cloud, private connections to the cloud, and we provide the whole digital infrastructure which is necessary for companies to become digital. We have more than 220 data centers over the world, and that's why we can provide the whole global infrastructure. So how important are data centers? I would argue that data centers are a critical function in society today. Digitalization is progressing extremely fast, both on the private side, but foremost, companies are also becoming more and more digitized. And digitalization is completely dependent on co-location and hyperscale data centers. We can take internet as an example. Internet would not work without the colo providers. It is in our data centers that the network service providers are exchanging traffic with each other, which is the basis for internet. It's also in data centers that enterprises can connect to the cloud and to the ecosystem of vendors, partners, and customers that enterprises need in today's digital world. It's also from data centers that all digital services that you and I use in everyday life are delivered. So whether you do an online purchase, a credit card payment, a bank transaction, maybe you watch film or video online, you watch news online, you play an online game, maybe you use digital healthcare services. All these digital services are delivered from a data center somewhere in the world. If we take technologies in the forefront and technologies which are important for companies to stay relevant, to stay competitive, I'm talking about technologies like AI, IoT, 5G. These technologies will not scale with a centralized approach if they are installed in a central data center somewhere. And the reason is that these solutions, they produce and consume enormous amounts of data. And they will not scale if data needs to be moved over a long distance. And that is why enterprises today need a digital infrastructure which is distributed over the world where they have their users. So what we see more and more is that the traditional data center has played out its role, and enterprises use hybrid solutions with colo and hyperscale data centers distributed in many places in the world. So COVID-19 has, of course, had an impact on all of us. And COVID-19 has been a massive disruption to many companies. Because companies were suddenly faced with a situation where a big part of their workforce had to work from home, meaning that fully digitized services were more crucial than ever. And all this has been driving a need for increased interconnection and services delivered by co-location data centers. Also, if we look at healthcare, healthcare is also changing behind the scenes. Artificial intelligence, machine learning, and Internet of Things are vital to new strategies for virus surveillance and diagnosis. And if we take AI in particular, AI is helping to power digital assistants, drones, and robots that are being used to improve care while reducing risk. And as I mentioned briefly before, AI and IoT needs access to the cloud. They need distributed architectures. So colocation and hyperscale data centers are very important when launching these type of solutions. So what are we doing to protect the planet? Well, the data center industry has been very criticized for using large amounts of energy, large amount of electricity, which is also true. So it's really, really important that we as an industry take this serious, and I think we do. The whole industry are focused and obsessed with operating efficiently, both because it represents cost, but I think also it fits the ethos of our industry of always trying to do things better. The efficiencies are twofold. The first one is that we continue to design and operate our data centers to a standard that in fact makes us operate twice as efficient as a traditional data center. And this has been measured and documented. And I think George also mentioned it in his presentation. What we also see when enterprises move their workload into a cloud or colocation environment, we've seen enterprises can achieve at least 2 to 3 times the compute capacity on the same number of servers. As a company, Equinix has made a commitment to go 100% green. At Equinix, we achieved 92% last year. And because we are the biggest data center provider in the world, we have 220 data centers spread over 5 continents. And if we become more efficient, if we become green, of course, that has a big impact on the industry. And we are continuing to push to go green. As a company, we have invested more than $100 million in renewable energy programs. So we are focused on efficiency. We are focused on going green. And by that, I would like to thank you for listening to my presentation today. And I think there will be an opportunity to ask questions.
Very much. Yes, there will be an opportunity later on, but I think we go straight over to Thomas from the Business Sweden, please.
Thank you very much. So, in view of time, I'm sure people are ready to go and have dinner if you already haven't gone to dinner. So let me quickly take you through some numbers so that we can see the size and scope of the data center industry in Sweden. I will briefly touch on the context, the Swedish data center industry from the outside. Then I'll talk about the Swedish data center landscape and provide you plenty of numbers, figures to take with you to digest by yourselves. And then mention towards the end very quickly what's around the corner, what's next. So in a European context, it's very important to view what Europe looks like in terms of the data center industry. And we have if we look specifically at the commercial data center industry, which is much easier to measure than the rest, we can see that in Europe, 4 cities, Frankfurt, London, Amsterdam, and Paris, account for more than 2/3 of all the installed supply of data center capacity in Europe. That's a huge number, approximately 1,700 megawatts of installed capacity in those 4 markets, growing annually now roughly by 180 to 200 megawatts, according to the latest numbers. There are a few locations which are quite interesting and new and upcoming. Dublin is one of them, growing very fast on the back of a lot of hyperscale investments in the market. And Stockholm, where we are right now, is the second location, which is very interesting from an international perspective. Arguably, this location, Stockholm and Sweden, is the one that maybe shows the most promise in terms of sustainability. If we look at the grams of carbon dioxide per kilowatt hour produced in our national mix, we see that we stick out extremely well in this context, and that's maybe what makes international players to look closer at Sweden and the Nordics. And so if you only bring back 3 things from my presentation today, one is that Sweden is growing, but it is growing from a very low level in an international context. Energy efficiency in Sweden is high, and the future growth in Sweden thus promises to become and be very green, be very highly energy efficient, however, very difficult to estimate. But let me come back to those numbers in a second. If we look from the outside again, just taken from a commercial database of data centers across the world, this is how the world views Sweden. They think that we have roughly 86, well, let's say close to 100 data centers. We have some 200 service providers, ISPs, and communications networks, and some network fabrics. But the thing I'd like to focus on here is really the role of the large metropolitan areas, the capitals, the hubs where connectivity is found, which is so important, and why these become such critical points in the networks and in the data center industry. So look at how big a portion of this industry that is here in Stockholm versus the rest of the country. Very recent numbers. I will be sharing numbers from a report that has not come out yet. The report will come out on November 17th. It's done by Radar Group, and the data was collected during May and June this year. So first numbers I'd like to share from that report is the energy efficiency of data centers. This is a very rough measure, but it is a measure that is used across the industry, so it gives at least indications on what kind of energy efficiencies you can expect. And the things I'd like you to take away from this slide is that Sweden fares fairly well in terms of comparing the energy efficiency with Western Europe and North America. But the more important is that the more industrialized the data centers are, the better energy efficiencies do you get. So the colocation sector, the commercial data centers are much better than the traditional data centers. And if you then also scale it up like the hyperscalers do, then you see that the energy efficiency goes even further down. And globally, of course, this is happening. It is reaching a plateau as the numbers seem to have evened up towards the last few years. So let's look into Sweden specifically then, and here are some numbers for those of you who like them. This is data directly collected from the market, from the players here in Sweden, and added on to models to estimate whatever data that was not being answered directly by companies. So you can see that the entire data center industry in Sweden consumes 2.4 terawatt hours approximately. The commercial sector, the colocation sector, is the largest one still bigger than the hyperscale sector. And we can also see that this corresponds to roughly an installed used capacity of 270 or 280 megawatts, which is reasonable. The numbers we saw in 2015 were approximately 220, so this has grown a little bit in the past 5 years. This becomes even more interesting if you look at the utilization rate of the data centers. Again, these are numbers from the same report by Radar Group. You can see that traditional data centers have a very low utilization of roughly 24%, whereas the commercial data centers are much higher, three times as high in the hyperscale segment, up to over 70% of utilization rate. And that's where we get the efficiencies, the lower costs, and the energy efficiencies of these facilities. As a perspective, just to compare numbers, so the entire digital footprint of networks, equipment, and data centers in Sweden corresponds to that green box on the slide, which is then compared to Sweden's total industrial electricity consumption on the left. So it's not unreasonable, I would say. If we then look at the industry structure, that has changed a little bit since the last reports that were done 5 years ago. We have seen a growth. Industrialization has grown, which means that the bigger facilities, there are more bigger facilities, which is of course the commercial sector that's growing, colocation, and also hyperscale. And we also see the base maybe contracting. This is maybe difficult because there is no specific data from all these 2,000 companies out there, but there seems to be evidence that this has contracted a bit since during these past 5 years. Looking then at the geographical distribution across Sweden, it becomes even more interesting, I'd say. This is looking at the installed capacity now, so there's a little bit of caution. We're not looking at the actual used numbers, but the installed capacity of data centers for the different electricity price areas. And we see that there is a lot of capacity installed up north, not so much in SE2, quite a bit actually installed in the greater Stockholm region, based on the fact that I just presented that the colocation, the commercial market is so big in the capital, and then very little in down south. If we then look at the projected numbers, these are of course very difficult, but this is asking companies how much they intend to or plan to grow over the next 5 years. We see that there is a good amount of growth up north, almost 100% growth, so a doubling of the installed capacity. Huge growth in the south. And I'd like to comment on that because I think this is really important to understand, that this is really driven by companies and their strategies and their client base and their partnerships and where they have their markets, so to speak. So all these decisions about where to locate data centers is really based around corporate strategy, technical decisions, and commercial decisions. So that's why this big request for demand, I would say, I would call it almost in SE3 going forward. If we look at the segments, these are quite surprising numbers. Growth, of course, depends on very many parameters. Like I mentioned just now, very much demand-driven, but also a lot dependent on market movement, outsourcing trends, consolidation, technology improvements that we'll touch more on in the next speaker, and so on. The two things that I would like to point to in this slide is that, surprisingly, the in-house or the traditional data centers are projected to contract, but only a little bit up to 2025, only 0.5% down, which is contrary to most of the global predictions and analysis that have been done in other markets, where Gartner, for example, predicts that by 2025, 80% of all the traditional in-house data centers in the US will have moved to commercial colocation or hyperscale or a mix thereof. The second thing I'd like to point to in this slide is the fact that, as you can see, the lion's share of the growth comes from the hyperscale sector, and the capacity demand there is very much demand-driven, and so it's very insecure or uncertain, rather, how much of that growth will happen. So it's much more predictable maybe for the commercial sector, as you can see, colocation and system providers and system integrators down below. And to round it up, bring it back up again to an international comparison, if we compare Sweden then to some other large markets in Europe, we see that, for example, Netherlands, which is a hugely successful digital nation with very connected data center infrastructure, that market is bigger in all aspects than the Swedish market by several factors. Commercial data center market is maybe twice as big over there. IT space footprint 2.5 times as big. Power-wise or capacity supply-wise, you can see that Amsterdam has about 7 times the supply of data center capacity, commercial data center capacity, than what Sweden has or Stockholm has. So that's a very significant number. Germany, which is a very industrialized country with a lot of manufacturing spread out across the world, across the nation, has approximately 20,000 facilities, which is a very big number, very well analyzed over several years now. A huge commercial market, of course, surprisingly enough, the employment figure that was just updated last year from the previous figure that was 3 years old, which was approximately 200,000 people employed in that industry in Germany, was now upgraded to 210,000 last year. And I think those numbers are quite interesting. If we look at Sweden, we've had a lot of interest from media recently about employment numbers for the data center industry. Unfortunately misquoted and misrepresented the previous reports. I think the correct number that should be looked at and should be used is the number that I've put up here, approximately 2,800 people in 2015, so 5 years ago, that were involved in data center operations in Sweden. So around the corner, there are much better people to talk about that than I am, but just let me mention a few quick things. In the left corner, you see the hyperscale data centers. This is going to continue. We now have 540 hyperscale data centers in the world, out of approximately 7.5 million data centers globally. That's not a big number, but that's growing. But the big thing that's going to happen next is, of course, the edge computing, bringing the computing power closer to the various applications that Maria and Jens and Anders and George were talking about earlier. Edge computing will move out closer and out into the society, here illustrated by lamp posts and some container behind the supermarket maybe. Some analysts actually predict that half of the new installed digital infrastructure by 2023 will come from edge deployments. Half. That's a number that's going to challenge most of the thinking that we've seen so far in what we call the data center industry. That was all for me. Thank you very much.
Okay, thank you very much, Thomas. And I think Maria is also with us. Yes. And I think I got some of the answers that I posed in the beginning, why is it important where to locate data centers. And I think you, Maria, stated it quite clearly. And you, Thomas, talk about the company strategies and so on. Because, I mean, there's really high numbers that you are now estimate in the middle of Sweden. And, of course, we know that we have these capacity problems. And so how do you see on this? It has to be solved somehow? Or because we know that there are a long time scale to build new lines and to get this solved. But how is the discussion going from your point of view?
Well, in our role at Business Sweden, we talk to a lot of different companies. So, of course, each company has their own strategy, and we're trying to help them discover what there is to see in all parts of Sweden. Naturally, there is a big interest in looking at the large metro areas, and also more recently in the southern parts of Sweden. And there is no magic to be done there, of course. We talk a lot with the energy companies, we talk a lot with the Swedish grid owner, Svenska Kraftnät, and we're trying to find places where there is enough capacity to build these facilities. this is all done in international competition. So if we can find a good place, then we'll see the establishment in Sweden. If the conditions are not right here, then those companies will go elsewhere.
Okay, and Maria, you talked also about the need for the quick to delocate the different data centers and to have that as an important way to have a quick interaction with the data and so on. It's because there's a lot of in the media saying, why can't you put these data centers in the north instead? Is that an issue that you are discussing? Is Maria there?
We can't hear Maria.
I can't hear Maria. Have you muted?
Yeah, no, sorry,
No,
I was
sorry.
muted. Yeah,
Okay.
Yeah. No, I think that's an interesting question, and we normally place our data centers close to the big metros, and it's all, physics. To determine whether we could have edge data centers in the north, for example, the way to determine where a company needs to have their hubs, and with a hub I mean, some sort of installation in a data center. The best way is to analyze where are the users, where are the connected devices located, and then you need to look at response times. You need to look at data, the speed of data transmitted in fiber, and the amount of data to be transmitted. And that's how you can determine where your data hubs need to be. So it depends. It depends on the application. It depends on the response time needed. And that's very, very different. I mean, we talk to companies sometimes in Oslo, and they cannot be located in Stockholm because their response times would be too long. So, and for other applications, it's okay. So it's very, very different, and it's different for different companies.
Okay, I think that's the clarification.
Yeah.
Good. I think Linda, you had some question about also how do we attract these data centers to Sweden?
Oh, yeah, and also we have a question, I think, we have a question on the taxes surrounding the data centers and the energy consumption, the deduction of taxes for the data centers. I don't know if maybe Maria would like to say something, clarifying.
Yeah, I can comment on that. And I think Thomas is also very much aware of the situation. There was a tax reduction for data centers that was actually changed, I don't know if it's a year or a couple of years ago. So the colocation business cannot benefit from the tax exemptions anymore. But the very large hyperscale data centers can still. I don't remember exactly what the limit was. Thomas, do you remember that?
It's 100 kilowatts, so it's not really very high. The change in legislation was that now I think the energy tax, the consumer of the equipment has to take
exactly
that.
The customer needs to ask for the tax exemptions themselves from the tax authorities. The data center would not be able to do that.
Okay, but for hyperscale it's possible.
It is possible for really, theoretically, for all in the industry structure that I showed you. Roughly 175 companies in Sweden, we think, are eligible to get this lower energy tax, which the entire industry gets in Sweden, manufacturing industry. But then there are some exceptions or tricks that you have to apply to actually get that whole discount. And most of those companies, of course, are Swedish companies. So.
Okay, so can you say something about what was the goal behind the change in that?
I think you'll have to ask that of the politicians and the people that changed the legislation. But I think it was clearly a if you looked at the surrounding environment, we had countries in the Nordics all changing the energy taxation for the digital industry. And as the digital industry has become industrialized, what I was talking about, then of course they should have the same conditions as the rest of the industry in Sweden.
So maybe Jens, you could also join here, and also maybe if George and Anders is listening, because I think now I want to come into the research side, and there I wonder if you have any where you see from data centers, but also you, Jens, looking for a more broader perspective. Where do you see the most important technologies development needed, and what are from the Swedish research area? Do we have any? Do you see any or focus there that we are on the top agenda, or where do you see the most important issues?
I think for Ericsson it's quite clear. 5G.
5G
is of course what we promote.
Yeah.
And I mean the data capacity of 5G actually outperforms fiber in many areas. But fiber, of course, you need fiber to the 5G base station. But you could actually start to. It could become like one network standard. 4G works very well, and I mean the standard itself is not tied to any frequency, so you can deploy them on low frequency. So you actually can cover rural parts, and Sweden and Finland and Nordics are quite sparsely populated with large areas. You can have 4G and 5G there as well. So that and of course we are also looking into AI and edge computing and cooperating with a lot of industries, because before it was more like a consumer thing, but now with these high data capacity, industries start to also look into, we can have our own systems here and be very efficient inside our manufacturing facility and so on. So it's a very interesting area. And one goal, of course, is to become much more efficient and in the end save energy for I mean your entire production or what it will be. It could be for Volvo and others to operate cars very efficient.
Yeah. George, do you have any views of the main technologies development important for this area?
Yeah, I think it's a great question, and I think nobody can accurately predict the future, but I think we could see some of the trends emerging at least. So, like more and more workloads around artificial intelligence and machine learning. There's been some emerging papers that have tried to quantify the carbon footprint of training machine learning algorithms. Again, I think for some of these applications, we don't really need, we don't really run into latency issues, I think. Or we can try to shift some of those workloads where we're doing machine learning training to regions that have very clean electricity, or overnight when there's maybe a lot of wind available and no other demand sources. So I think trying to optimize how we shift around different data center demands could be quite interesting to try to lower that footprint. But yeah, machine learning, blockchain, IoT, and then all these kind of applications that are built on top of these digital technologies. So, you mentioned edge data centers and 5G contributing to Internet of Things and connected and automated cars. And that opens up another whole discussion around the energy and environmental impacts of automated cars, which could go, it could save energy or it could increase that energy use and emissions. So it's these layers that we need to be careful and to think about. I think it's very important to focus on reducing the carbon footprint of the digital sector, and we can't forget that. But also we need to think about how these technologies are used in other sectors, because arguably that could have a very large impact on our global greenhouse gas emissions. There was a question earlier about whether we should look at energy intensity or efficiency metrics about kilowatt hours per compute. But I think what the planet cares about is the absolute number of greenhouse gas emissions that are emitted. So, whether we're increasing efficiency at a very fast rate, what really matters is the absolute emissions that are coming from digital technologies, coming from transport, coming from buildings, coming from industry. And we need to get those rapidly towards zero. So we're working in that kind of context where all sectors really need to contribute. And I think digital is an interesting one because not only is there a direct footprint, which we need to reduce to zero, but there is this potential to accelerate the reduction in other sectors. And I think that's where some of these companies with very large resources, technical capacity, I think they should be looking more and more at how can they play a part in reducing the carbon intensity of electricity grids. Data centers have a very flat demand profile. Can they start shifting around demand around whether there's wind available or things like that? So I think it's several layers that we need to talk about, but really guided by strong climate policy, I'd say.
Thank you very much. Well, Maria, do you have any comments there? Can you, as the biggest company, shift around the data?
Yeah. Well, I agree with all the previous speakers. All these technologies are really important for us and for our industry, like 5G, AI, machine learning, IoT. To be in forefront in these technologies are really, really important for our industry. And I think initiatives like AI innovation is really important so that companies can get help and get support when they work on technologies like this.
Okay, I think though we have to continue, and I will really thank you very much, Jens and Thomas and Maria, and also Anders, and we will go forward to our last speaker, and that is now we're getting more into the research and technology development and what can we expect for the future. And I know that Professor Lars Thylén will make a presentation of what is happening, and he will actually look into this. What is how much energy the data, a piece of information, to transfer a piece of information takes, and what are the possibilities with new technologies. So I welcome Lars, and we have a possibility to pose some question afterwards. Thank you.
So this talk will shift gears a bit. It's entitled A Brief Look into Possible Developments in Electronics and Photonics for Data Centers and General Applications. My name is Lars Thylén, if you pronounce it in Swedish. Professor Emeritus from Photonics and Microwave Engineering at KTH in Stockholm, and a current affiliation with Department of Theoretical Chemistry and Biology, also at KTH, and I'll get into that towards the end of the talk. And a data center close to the polar circle in northern Sweden. Power input to data centers, low entropy energy, is much larger than megawatt, and signal output smaller than the megawatt. And the difference is basically high entropy thermal energy. And that's exactly what we want to diminish. And then a quote from a Stanford colleague: the growth in the amount of information processing and communications in data centers cannot be sustained without major reductions in the energy per bit. And energy per bit is something I will talk about. And let's have a view on internet traffic. Something that surprised me a number of years ago is that most energy dissipated in electronic machines is used to communicate. On silicon chips, 50 to 80% of gates are for the repeater amplifiers in long interconnect lines on chip. But much more data is sent over shorter links, for instance, within data center. For 10 to 6 bits communicated inside the data center, only 1 bit is exiting. Okay, so which electronics and photonics, photonics is photons instead of electrons, a colleague of mine remarked, can mitigate the increasing energy requirements in data centers and also elsewhere? Well, materials have always been a key and still are. You all know what is in use. Novel materials such as 2D graphene, silicene, and metamaterials. Meta means beyond in Greek. And the properties are determined by man-made structures. These are extremely interesting.
And let's have a brief view of electronics. Current transistor-based electronics, 3D, FinFET, etc., is developing rapidly, as we will see. Molecular electronics, I'll skip over. Quantum computing, issue there is operation temperature below 1 Kelvin and not general purpose computers. Optical computing seems to be something of the past. Neuromorphic computing is quite interesting. One tries to mimic the human brain and integrate electronic and photonics. And I recently saw Intel scales neuromorphic research system to 100 million neurons, but it's beaten by far by the human brain. Electron waveguide-based devices I will talk a bit later on about. And one thing which is very interesting is reversible computing, because if you don't have reversible computing, if you erase bits, you sacrifice 18 milli-eV energy. Okay, so the trend of minimum transistor switching energy has decreased exponentially over the years, and this is a very interesting graph of what has happened. And at 2020, we are down to very low numbers, as you can see. The interesting thing is that there are some limits that are difficult to pass, which I will go into a bit more later on. Another type of electronics is here, where you actually use the wave properties of electronics. We got the idea from the optical digital switch, where you, in essence, have an input waveguide and 2 output waveguides. And by applying a field, you can make the stream of photonics to go to different outputs. However, you can do the same trick for electron waveguides. Then you treat the electrons as waves, and you have similar behavior, quantized conduction and so forth, in this case. And this switching was experimentally demonstrated by KTH at 4K temperatures and in 3/5. And it's configurable for reversible computing. That's the reason for the still present interest in this type of device. And room temperature operation, that is the great question. Can probably be done. And let's go over to a brief view of photonics. Like for electronics, we have a number of materials and implementations. We start from the left with a continuous wave laser, and it can be modulated also. Then we have a modulator. We have something in between, and we have a receiver and the output. And this thing in between is interesting. That's space switches, wavelength division equipment. That's actually where we have all these sort of things that make the network or make most of the network in a data center, with all the possibilities that this sort of offers between the different sources and receivers. And if we really want to have low energy per bit, it appears that we need to use nanophotonics and new materials. And that brings me to integrated nanophotonics in the 21st century. The term integrated optics was sort of coined as a parallel to integrated electronics, and today it's called photonic integrated circuits. And the original idea was very much the same as in integrated electronics. You put the devices on a chip and have a number of functions there, modulators and switches and so forth. And after decades of development, to the left we have an photonic integrated circuit, and to the right we have an electronic IC. And photonics is far behind electronics in complexity. Is it catching up? Yes, the nanophotonics, it is catching up, but in terms of complexity, I think it can be comparable to electronics, as we will see, but I think that computation and storage is something that electronics will be used for in the future also. So, and this is a graph of the inverse of the footprint of some integrated photonics devices. Starting from the lower left, we have a 4x4 switch in a ferroelectric material called lithium niobate. Then we pass over to 3/5 4x4 gate array switch, which includes optical amplification, and then we moved to the silicon field with a silicon arrayed waveguide grating and hybrid then to metals or plasmonic devices, hybrid plasmonic waveguide, and then to hybrid plasmonic disc resonators, all this at KTH and or Ericsson. But if we look at the theoretical possibilities, we see here at the top here, we see, for instance, near-field coupled quantum dots. I'll talk about that a bit later on. And also, if you have a nanoarray of metal nanoparticles, we also get a very, very low footprint device. So nanophotonics offers, as the name sort of implies, a very good possibility to continue this curve. And some routes to nanophotonics where the device size is smaller than or much smaller than the light wavelength. Well, for metals, it's gold or silver. They have the required negative relative permittivity, but they have optical power losses that are excessive for nanoformat. We have arrays of coupled quantum dots, QDs, artificial atoms, but requires keeping our wave phase between the quantum dots. This is quantum mechanics. And then we have the new 2D materials such as graphene. What can they do for us? That's an open question still. Just an example of what has been done. This is KTH stuff. This is a hybrid plasmonic waveguide ring disc resonator. And you can see to the left here, the device, it's built up by silicon, gold, and quartz. And in that way, we have an input waveguide, and we have the ring resonator, or disc resonator if you wish. And you can also see the sort of filtering characteristics of this. It's a narrowband band drop filter. And if we look a bit further on, the experimental Q value for this disc resonator with a radius of 0.5 micron is 130. The theoretical value would be 700 if we didn't have the inherent losses. And this device was, for a number of years, the smallest demonstrated integrated photonics device, worked by KTH. And then we have something else here. If you've been to St. Paul's Cathedral, you have probably also visited the Whispering Gallery there. And this is pretty much what we have here. We have a disc resonator, and we have metal and dielectric, and the light is trapped. If I can get this working. The light is trapped, for instance, here, and then it's sort of circling around, and it's extremely well confined. Now, the Q value of this will depend on absorption and radiation. And if we just look at the radiation, we see that even for a radius of 50 nanometers, we can have very high Q values. So the big thing, great thing is to get rid of the losses, or at least decrease them. And the so wanted new and better negative relative permittivity metamaterials, one can also formulate a Q value for these materials. So actually there are few attempts so far, and equally few to prove impossibility of zero loss negative epsilon materials. And to paraphrase Archimedes, give me a low loss negative permittivity material, and I shall not maybe move the earth, but revolutionize photonics. Okay, so another route to nanophotonics is to have coupled quantum dots to create a waveguide. And this is what it looks like. I won't go into the equation, just showing the three coupled quantum dots here. And you can see the dimensions are very small. And in order to keep them at the right distances and so forth, the idea has been to position them on DNA molecules. This is a collaboration with the University of Tokyo. And I've been in the area of photonic devices, integrated photonics, for about 40 years or something like that. And this is the first time I see something that can actually compete with CMOS. The quantum dot array photonic device is in theory comparable with footprint and switch energy, albeit at 77K to CMOS, but not in speed for single arrays. And 77 Kelvin is not forbidding. We can increase that. How much is an open question. And I won't go into this in detail. For the near-field coupled quantum dots, we have a switch energy about 8 attojoule, and for typical CMOS, according to the literature, around 20 attojoules. So CMOS is very fast per se, but it's slowed down in circuits by the interconnects. And that brings us to a very important point. Namely, there is something unique in photonics applications in ICT technologies, and that is interconnect. And if you remember, I've shown this before, most of energy dissipated in electronic machines is used to communicate. And I have to explain it a bit more. So what you see in this slide is you see metal here. This is a metal piece, 1 centimeter by 2 millimeter. Information is coming out of the screen, and here you see the corresponding photonic waveguides. And if I calculate the capacity, the total capacity of this metal and the fibers, it turns out that the total capacity, even for 1 millimeter transmission, which is what I used for calculation, even for 1 millimeter transmission, photonics and metal are comparable, and metal falling off very rapidly for longer distances. And this should have a big impact on architecture of electronic photonic systems. Okay, so power dissipation and data centers, returning to that, you have seen this before, the growth in the amount of information processing and communication can't be sustained without major reductions in energy per bit. So let's see what is the energy per bit here. Let's take electronics. Present CMOS approximately 5 attojoules, theory approximately 0.2. But from the web, I mean, using adiabatic principle, Sandia Labs has been able to reduce energy by 85 times. And next point is reversible logic, as I was talking about before, seems to be emerging as a practical option for continued scaling. And so you can see the intense research going on. But there is actually a limit down at the end of the page, limit on energy per bit for low error rate. Generally, and the question is whether it's generally applicable, and that is 60 kT, which is around 0.2 attojoule. And this is due to the fact if you want to have low error rate in complex systems, you have to require at least this energy. So that sets a lower limit, so to speak. Let's look at photonics. According to Stanford, the picojoule per bit, which we have today or something like that, should shrink to 10 femtojoule per bit, okay? Light modulators, theory approximately 0.5 femtojoule. Within reach, with improved plasmonics, experiment about 20 femtojoule per bit. And the laser, there my colleague Richard Schatz has made a very much more complete job than myself. And there we see, if we look at the table here, at state-of-the-art results, 4.4 femtojoule per bit at 10 gigabit per second. However, if we go to higher bit rates, 275 gigabit per second, the bit price is very high. So in summary, in photonics as well as in electronics, the goals in energy per bit are probably reachable. So let's return to this once more. Such growth in the amount of information processing, etc., can't be sustained. But there are other possibilities. Replace power-hungry electronics, time division multiplexes, by space division multiplexing. Replace clock and data recovery by synchronizing photonic pulses in the photonic domains, making the whole system look like on-chip interconnects, up to and beyond entire cabinets, both functional and in their energy use. And the optimal interface, this is very interesting, photonics and electronics moves closer to electronics, a case for nanophotonics and a new architecture paradigm, and monolithic integrated photonics circuits, called EPIC, maybe. Okay, so a more holistic approach will not only have to take into account new materials and new hardware concepts, but also, of course, architectures of whatever system and software. And one example here of research going on, this is at Princeton, Neuromorphic Photonics and electronics, again involving the brain. We have here microwave, analog photonics, silicon industry, and scalable computing models. And these two circuits can be connected by free space linear integration and so forth. And the neuromorphic electronics can be used on another leg and finally, integrated RF photonics can be used to bridge analog photonics and silicon industry. Interesting thing is that you have neuromorphic photonics in the center of everything here, and this is extremely interesting in the sense that you combine the different technologies and try to use the best of each of them. In the 50s, turning to something else, but related. In the 50s, there was a very interesting talk given by Richard Feynman. There is plenty of room at the bottom, and we should use it. What he meant was that he considered the possibility of direct manipulation of individual atoms as a more powerful form of synthetic chemistry than those used at the time. And the talk went largely unnoticed. But this was the sort of introduction, in a sense, of nanotechnology. And inspired by that and other things, I think a route ahead would be bridging the gap between atom and microscales in pursuit of new, more efficient metamaterials. So ab initio calculation of properties of micro-sized structures from properties of nanostructures, and implementing new monolithic photonics integration in these nanostructures. And this is from the department where I'm currently. This is theoretical modeling, Department of Theoretical Chemistry. And we have basically all we need: algorithms, applications, devices, processes, and so forth. And the capability also to model for instance, the electron waveguide I mentioned, but also the near-field coupled quantum dot, modeling them from the basic atoms to predict some properties of devices. And that, of course, requires large computer resources, and that is exactly what is being developed in the world at this time. And next year, there is planned a comprehensive EVA seminar on these fields: interdisciplinary research, nanophotonics, nanoelectronics, and their monolithic integration, bridging the gap between atom and microscales, and for decreased power consumption in ubiquitous applications, and where we will look in depth into these issues. Acknowledgement to a large number of collaborators you can find here. And that was it. Thank you.
Thank you, Lars, very much. Very insightful. I'm not able to pose any more direct question on the theories and so on, but are you there, Lars? Yeah?
Yes, I'm here.
Good, thank you. I just have one question. What do you see the time scale for this type of technology and the possibilities to go forward?
That depends on how much money you put into the research and how you coordinate it preferably internationally. It's interesting, in the first talk there was mentioned the Landauer limit, and it's interesting to know from information theory and from physics which are the fundamental limits, if there are any fundamental limits, and I pointed to some of them because one shouldn't try to get below these. It's not a good thing to do. What I see as most interesting is, and not only for ICT, but equally much for bio and medicine, is the nanophotonics and nanoelectronics brought to much smaller dimensions, which will increase the versatility of their use, but also hopefully decrease the power consumption. And we have seen for the big per energy, seen this continuous decrease going on, and it will go on for couple of years or decades more. And but we will have to start to look at some of the things I suggested, and maybe not only try to improve existing technologies.
Interesting. So, as you say, you see these possibilities in other sectors, as you say, as medicine and also, and I think that is, of course, of great interest. But do you see the Swedish research in this area? Are we ahead there, or are we more? I mean, is that what, or as you said, we need more money to focus on this. But how is the position for the Swedish research in this area?
Well, to the best of my understanding, it could be better, to express it diplomatically. And I think that it's also a task for Eva to see to it that one do this sort of looking into the future and see what the different technologies will mean. I've spent a number of years at Ericsson, and we had the sort of view that it's even if we don't make the devices or hardware, whatever, we have to know what is around so that we can build the systems. And that I think is a very important aspect. So learning more about this and understanding what the development in our surrounding world and hopefully in Sweden will mean is very important. And that's why I mentioned about this seminar that we are planning to try to cover this in more detail. One of the most fascinating things are, of course, the neuromorphic stuff. That has been around for some time, but maybe not given so many results. But there are all sorts of possibilities.
Yeah. Thank you very much, Lars. And I think really you have given understanding why it's important to go further in this. And we will, of course, highlight that in further work in EVA. I think that I will propose that. So that is, you can see this is as a start for next year's big seminar, more in depth for theory. So with this, and I know we are a bit late, but we have got more questions via the Menti, and we will sort this question out and answer them, and you will get answer via mail. So that's sorry, but this is the situation. But with this, I like to close and thank all the participants and all the audience. I know there's been a lot on the web looking, and so thank you very much, and for the future, and hope to see you, Lars, and others for the next seminar. Thank you.